let's move on to the next problem. But yeah, this one was pretty easy. I agree. Let's try this one. So D and E are on AB and AC, so that DE is parallel to BC. Okay, so we have some flexibility here. And then we draw the intersection of DE and CD. That should be P. And then, so we have APD and BCD. That's a little weird. So that would be M. And then we draw APE and BCE. So that's APE, BCE. That would be N. And then we have a circle through M and N tangent to BC. I don't even know if a circle like that exists with this diagram. So let's see. Yeah, how do we make a circle like that? Let's see. So is there a circle? Let's see. If I make this, yeah, maybe I need to make it more like of an acute triangle, kind of like that. Then a circle should exist. So let me think how I would draw that. So its center is going to be on the perpendicular bisector of MN. And yeah, how do I draw that? So a circle through M and N tangent to BC. I know this is like some famous Apollonius problem or something, right? Where you want to draw a circle through 2 points that's tangent to a certain segment. So yeah, I could try to just eyeball it, but let's think a little bit first.
Or you can just draw a random circle and then you pick the intersection of the two tangent, like the problem as.
So draw a random circle where? Through M and N or?
Yeah. And then you see if the intersection of the tangent meet on AP, and then you can find the center.
Okay, so if I take this circle, let's say, and I draw the intersection of which tangents? The tangents at M.
Yeah, M and that circle.
Okay. Okay. So are you saying I want to kind of see when the tangents meet on AP?
Yeah.
It almost looks like the tangents, so okay. So really, really I want to draw the intersection of AP with the perpendicular bisector, right? And then I want to take this point right here. So let me delete the circle for just a second. So I would want to draw the circumcircle GMN, right? Oh, did I? Let's see. Okay, so this circle, if I draw this circle, then the tangents intersect on, or I think they intersect on AP. Let's see. Maybe not. No, I got a little confused. So let's see. Let's see what I did. So you're saying you draw a random circle through M and N, and you draw the tangents at M and N, and you want them to intersect on AP.
I just tried something and it works.
Okay.
Basically, the midpoint of BC is the tangency point.
Oh, really?
Yeah, that looks true from the diagram.
Interesting. Okay. So if we take the midpoint of BC, so obviously AP and F are collinear, then we can try to show that that circle is tangent to BC. Interesting. One sec, guys. I'll be right back. All right. Thanks for waiting. So we want to show that this circle's tangent to BC.
So I just found something other which is important.
Okay.
And that is just that we can notice N is the Miquel point of FPEC.
Okay.
So that means that BPFN is cyclic.
All right. And then
it just looks better for the angles. And yeah, also we have that.
okay, so N is the Miquel point because it's the intersection. Basically, if we draw this, then we have the circle BPF, and if we draw these, then we have the circle. We don't draw the circle CAF, but we do draw this circle EPN or APN, and so, or APE. So yeah, the intersection of the circles APE and BPF is N, and so that's going to be the Miquel point. So yeah, and then we have other cyclic, right? A and FC should be cyclic. I don't have to draw all of them, but that makes sense. And yeah, BNEC is going to be cyclic. So yeah, so this is cyclic. So it's this.
I think it's best to kind of erase circles B, C, E, N, and circles APE and APD.
There's APE.
And also, yeah, the circle BDC. That is because we can define M and N apart from point D and E. So we can basically erase D and E.
Okay.
And define points M and N independently of them. We just need point P.
Okay. So
basically P varies on the median.
Okay.
And M and N are the intersections of the two circles already drawn and circles AFC. So we have AFC and ABF.
Interesting.
So now the diagram looks much better.
Yeah. Like that. So yeah, we just draw the two circles AFC and ABF, and we see where they meet BFP and CFP at M and N, and then we would just want to show that circle's tangent to BC. All right. So A obviously lies on the radical axis of these two circles. I don't know if it's worth drawing this point, or something. We'll just leave it for now. Yeah, we want to show angle MFC is MNF. So yeah, let's see. What if so P can be any point on the median. I'm just curious, if I move it, what happens to M and N? Okay, try drawing the center of this. Maybe GMAN is cyclic. Let's see. No. Does that pass through the midpoint of MN? Just guessing here. I should stop just guessing, but yeah. Yeah, I like the idea of getting rid of B and E. I feel like that helps a lot. But I wonder what, yeah, is it obvious for like a special case of P? If P is like the centroid, maybe we could invert. Sometimes that helps to show stuff as tangent.
Yeah, I think root BC inversion helps.
Okay. So let's see. We did a root BC inversion. B and C would be swapped, right? F. Do we know where F would go?
Yeah, it goes on the point on the circumcircle, which will be the AC median.
Okay. So let's see. Yeah, I could draw the tangents at B and C. That might be the easiest way to do that. So it would be, so F goes to that point, I. I'm going to call this I just so that other stuff doesn't get renamed to I. Okay. So F and J get swapped. So the circle ABF goes to the line BJ, right? And the circle ACF, well, first you invert and then you reflect it.
ACF goes to line BJ.
The circle ACF goes to line BJ, and the circle
Yes.
ABF goes to line CJ. And then this circle.
It can also be, it can be also easy. P goes to also just some variable point on DC median.
And is it true that PFJ in that point would be cyclic? Oh, it looks like PFJN. I don't think those actually concur. Actually, I think if you zoom in, yeah. So
yeah, but yeah, it is probably true that they're cyclic.
okay. So yeah, P would basically go to some variable point on AJ. So basically, if we pick a point on AJ, then let's see. So this circle, if H were the square root of BC inversion. So then we'd have BPF would go to CJH. So basically, it's like we would have the circle CJH and BJH, and we'd want to see where they intersect BJ and CJ. Is that right? And then so yeah, we just keep transforming the problem. So for a variable, basically we can start hiding stuff again, right? So let's hide point P, and let's hide F. I don't think we need F anymore. maybe we don't need M and N either. So basically, like all these circles through this we can hide. I think basically we have BHJ and CHJ, right? And we draw BJ and CJ. Are those actually, I would be very surprised if those are actually tangent. No, they're not. So if I draw BJ and CJ and they meet the circles at 2 points, I forget. So that's where M and N go to. Is that right? And then so we want to look at the circle KJL, I think, and we'd want to show its tangent to the line BC would go to the circle. With the line, what does happen to the line BC under inversion? So B and C get swapped.
It goes to the circle ABC.
Goes to the circle ABC. So okay, so we want to show that KJL and ABC are tangent.
Yeah, and by homotopy that is equivalent to KL parallel to BC.
Okay.
And I think we can prove that by another inversion.
Really? There must be a way with inversion, right? It looks too simple, or it feels too simple.
I agree, but
inversion.
I think I've seen something like this before, and you can do it by inversion.
Interesting. Okay.
So if you had a parallel line like that, so you wouldn't define it like in the problem, but you took a parallel line to BC and intersected with JB and JC. And then if you invert, at J, I don't know, maybe root BC inversion again, I think, just for triangle JBC, then you would actually get circles like this in the problem, I think.
Okay.
And basically, because median and C-median are isogonal, you would get the intersect on the C-median.
Okay, so you're saying you take a line parallel to BC.
Actually, let's say it like this. Take the midpoints of BJ and CJ.
Okay. Let me actually hide point I, because it's like we know that J is, we know that, yeah, J is the midpoint of this median chord. So, or J's, where the median chord meets the circle. So we take the midpoints of BJ and CJ?
Yeah.
Okay.
And then, by a homotopy at J, if you intersected circles BJQ and CJO, that intersection point, as you move a line parallel to BC, it will basically that intersection would stay on a fixed line through J.
So basically we're moving line KL is what you're saying?
Okay, let's say we move KL and KL is just parallel to BC. Okay. And then you took those two circles which intersect at H.
Yeah.
And then that H would lie on a fixed line through J just by a homotopy.
Okay.
Does that make sense?
Um, so basically, have you defined points K and L individually yet, or it's just some line parallel to BC?
Well, I wanted to do it with O and Q, but basically what I want to say is that when we intersect the circles including O and Q,
Okay.
we only need to show in that case that this point lies on the C-median.
Okay. Oh, so once you prove it for the special case by a homotopy, you would prove it in the general case.
That's what I want to say.
Okay.
And then I'm not sure if we do root BC or root BC over 2 inversion, but for triangle JBC. So we would do root JB times JC over 2, or not with over 2. I'm not sure which one of those.
Okay, so then C would go to O and B would go to Q. So this circle would go to the line OQ.
Yeah, but we don't need that circle ABC.
Okay.
Okay, so we do the inversion which sends B to Q and C to O, right? That is a root BC inversion. We reflect stuff in that.
Yeah.
Okay, then circle JOC just goes to line CO.
Yeah.
And the other goes to BQ, and then the intersection point lies on the median.
Okay.
That's why the other intersection is on the C-median, which basically proves what we need in the problem for the tangency thing.
Okay, because R would be the inverse of H. So H would have to lie on the sim-median from J.
Well, it isn't exactly H, but the top 1 point.
This point.
Yeah.
Okay, so then this point would lie on the sim-median from J. And
by commodity, you have for the any K and L that parallel, and you basically do just like the converse of that to get to the thing we need in the problem.
okay, let me think about that a little bit. So
yeah, it is a bit complicated.
So since JS is I mean that proves that these circles intersect on a J, right?
Yes.
Okay, so I mean basically we did like a root BC. Oh, because I see, because it has to be the midpoint so that like by Cheva's theorem stuff would work out. Well, actually, I don't even know if these have to be midpoints. Like, let's say it's like a third of the way, right? Then by Cheva's theorem.
Yeah. Any parallel line would yield median like that. But the midpoints are the easiest just to do for the proof with inversion, since you just take root BC over 2 or something like that. And in the other case, you would have to take, you would have to divide with other constant.
Yeah, so like if it was a third of the way, then it would just be a root BC over 3 inversion, and the proof would work the same, right?
Something like that.
So then if it's K and L, you could do a negative inversion. Like you could kind of do it in one step, but it would just be a little more complicated maybe.
Yeah. And basically the homotopy deals with that when we just do a special case.
Yeah. So okay, so I see. I see your proof. It makes sense. Before I type it up, let me just go back and make sure there's not like a really easy way to do it for this. So really, we could yeah, we draw these two circles, and then we want to show that KL is parallel. Yeah, maybe that is the easiest way. Because yeah, we want to show that KL is parallel to BC. It's the same as saying that if you start with an arbitrary parallel line and draw the two circles, that they intersect on the symmedian chord. Okay. So yeah, we could say consider an inversion about J. So I'm trying to think. Let's say we define it like this. If possible, I think we could do it in one step. So like, if we let this be like K prime and this be like L prime, then basically an inversion about J would take L prime, B to K prime, and C to L prime. And then we could reflect it. So let's think about that. And basically, we'd want to show that the circles, so it's like if we start with arbitrary K and L parallel, right? And we have an inversion that takes B to K prime and C to L prime, then showing that these two circles meet on the symmedian is the same as showing that what would it be? So would it be J K prime C and let me think about this. J K prime C and J L prime B? No, those aren't right. So these two circles, what would they invert to? So B, so B inverts to L, and then we reflect it. No, B inverts to K prime, which then goes to K. So K and B get swapped. So, oh, okay. So maybe it's the same as showing that BK and CL. Yeah, I think that's kind of what it's saying. That BK and CL, we want to show meet on the median, and that's true by Cheva. Okay. So, yeah, that would be how you would think about it, basically. So we could let BK and CL meet at a point, and then OJ is the median, so of BOC. So then if you do a root B, if you do a inversion about B, about J that takes B to K and C to L prime, and then you reflect it, then that would mean that since JO was on the median, then that would mean JH would have to be the symmedian, which would solve the problem. Is that right?
Yeah.
Okay.
And that solves the problem since, yeah, the end is trivial, so we can do it at the end.
Yeah. Interesting. All right. So let's start by saying let H be an arbitrary point on the symmedian chord, the A symmedian chord of ABC. Well, actually, we start with K and L being arbitrary. So yeah, so it's a little tricky to write up, but I'll do it. So let J be the intersection of the A symmedian ABC. And let KL be an arbitrary line. So take an arbitrary line parallel to BC. Let it meet BJ and CJ at K and L. And then reflect let K prime and L prime be the reflection of K and L over the angle bisector of KJL. Okay. Consider an inversion about J that takes B to K prime and C to L prime. Load by a reflection over the angle bisector of KJL. BKJ gets mapped to line BL. And CKJ to CK. So H gets mapped to BK intersects CL, which we'll call O. By Cheva's theorem, OJ is the median of JKL. And so JH is the median of JBC. By the inversion and reflection. And that means that H lies on HA. Lies on HA. Okay, so now we go back to the original problem. So hey Miguel, thanks for joining us. So we had a really interesting solution to this problem that uses like root BC inversion but twice. So if you go back to the original problem, we used Miquel's theorem a couple times. So P is the Miquel point of so let F be the midpoint of BC. So hello. So let F be the midpoint of BC. C, then the point P is the Miquel point of basically H is going to be the inverse of P, right? That's our goal here under the root BC inversion. So we had P was like a Miquel point of how did this work? Did we draw point N? So yeah, we had P and N, right? M and N. There's so much that happened that it's hard for me to keep track. So so we got rid of B and E because we knew that okay, P is the intersection of BE and CD. So N is the Miquel point. Let's draw that back in. Actually, I don't think it's so bad. So okay. So N is the Miquel point of FPEC. Miquel point, and well, it's not Miquel, it's Miguel with this joint, but so N is the Miquel point of CEPF. And M is the Miquel point BDPF. So basically CEPF, or sorry, CPFM and BPFN are cyclic. And so is ABFM and C. Oh, did I just accidentally erase? Yeah. So this means that we have a bunch of circles. So CFPM and BFPN. CFPM. BFPN. And then we have two other circles would be cyclic. So I think it's AFCN and AFBN. So ANFC and AMFB are all cyclic. That all comes from these being the Miquel points. So a lot of cyclic quadrilaterals. So yeah, we're definitely working backwards in this proof. And that all that information implies that P can be an arbitrary point on the median, AF, and it inverts to an arbitrary point H on AJ. So basically P can end up being any arbitrary point on AF, and it inverts to some other arbitrary point H on AJ. And so what do we want to show? We wanted to show that the circle M, so the circle M and F, so M would invert to, does M invert to K? Is that right? M inverts to K and N inverts to L. Let's see. So M lies on this circle, and it also lies on, what is it, ABMF. So M inverts to, once we do the root BC inversion, well, I should say after a root BC inversion at A. So if we do that, F inverts to J. So this circle inverts to line BJ. And this circle inverts to CJ. No, I don't think M inverts to J, right? This circle inverts to BJ. This circle inverts to C. Let's see. I'm missing something. So I think M, yeah, we want to figure out what M inverts to. Well, I guess it's clear. Like I would think M should invert to like some point over here. Let's see. So C inverts to B, F inverts to J, And yeah, now I'm confused. So was M supposed to invert to K? Because that doesn't look true. Must be missing something. So this circle inverts to line CJ, right? Circle ABFM inverts to line CJ. But this circle, I'm not sure what it inverts to. Maybe I just picked the wrong circle. So does this circle invert to this circle? Is that right? Now I'm confused. Oh, I think if we know that P inverts to H, then yes, this circle is going to invert to this circle. Oh, it just doesn't look like it because I didn't draw H to be exactly the inverse of P. That's why. That's why it doesn't look like it. So yes. So PFC inverts to BHJ. Okay. So PFC inverts to BHJ. After the reflection. And that means that M inverts to K and N inverts to L. There we go. So that's why it didn't look right, because I just didn't draw the figure right. So MNF is tangent to BC is equivalent to saying KJL is tangent to ABC. So by homothety, KJL is tangent to the circle ABC. Okay, so let's just finish this right now. So by a homothety, we have JKL is tangent to JBC. And that implies that M and F is tangent to line BC after the inversion. And that solves the problem. Well, I'll say that implies that M and F equals omega, which implies the tangents to omega at M and N intersect on AP. So yeah, it took a while to write that out. It's a tricky way of thinking about it, but it works. So thanks for the proof. Anyone have any questions on this? There's a lot going on here. So yeah, if you don't understand it, yeah, you could ask me after the session. So yeah, let's just make some room for, yeah, it's not, a lot of it's not super hard. It just takes a while to write it, to like explain it. There we go. All right, so let's try the next problem. This is from the Iranian Geometry Olympiad. So we have the quadrilateral ABCD, and P is the intersection of AD and BC. And we have two incenters. So this is like an if and only if problem. So yeah, I'm not sure like if we could draw like an exact diagram, but let's see. So I'm gonna make these lines and not rays just yet because so this is P. And then we draw the incenters of PAB and PDC. So those are both going to lie on the angle bisector of this angle. That's one incenter, and here's another incenter. It's going to be I1 and I2. And then O is the circumcenter of PAB, and H is the orthocenter of PDC. So that's kind of interesting. So those should lie on a line too, because, or actually, I'm not sure. No, actually, I don't think those will be linear. So let's draw the circumcenter of PAB, which is O, and the orthocenter. I don't know if I want to draw all the altitudes, so I'm just going to just draw the orthocenter itself. So okay, so it's up there, which is kind of interesting. I don't think, yeah, PO and H aren't going to be collinear. So let's see. So this is the orthocenter of PDC. We want to show that the circumcircles of AI1B and DHC are tangent. That's kind of a weird condition. Yeah, you have to really stretch the diagram. Let's see. If I do it like this, that might make it a little easier. So something like this, I think is good. So we want to show these are tangent. So that we want to show those two circles are tangent. Doesn't look the nicest because these points are kind of bunched up. But let's see if we can draw it some other way. So let's do it like that. So we want to show those are tangent if and only if AOB. Oh, now point O. Yeah, the diagram's not going to be perfect, but let's try to make it as good as possible. So we want these to be tangent. So we are saying those will be tangent if and only if AOB and DHC are tangent, or DI2C are tangent. Interesting. Let me put this on the next line. So it almost kind of looks like a symmetric problem statement. But it's not exactly, because like one's an orthocenter and the other's a circumcenter.
Then maybe we need to show that angle P is 60 degrees.
Oh, really?
Yeah, I mean, if that were true, that then AOB and like when the angle is 60 degrees, then let's say angle is 60 degrees, then the orthocenter of PAB and the circumcenter of PAB and A and B, they are on the circle.
Okay.
So that is like, you can angle chase that easily. But
does it really need to be 60? Like, I think we can still have these circles be tangent, even if it's not 60. So let's see. So like, it's
yeah, that is it is probable, yeah, that it may not be 60, but just you were talking about the symmetry, and it would be symmetric if we had 60 degrees.
Okay. Actually, sorry, you might, let's see, AI1B and DHC. Yeah, it's not a perfectly symmetric statement because you can make those tangent without it being 60 degrees. Interesting. All right, Raymond. Thanks for joining us. So yeah, see you next time. I feel like just because I put the word IMO in my video, I got more viewers. Yeah, I should title every video with IMO.
Oh, so you're starting clickbaiting.
Yeah.
Maybe we should then do one IMO shortest problem every session, and so you get more views.
Yeah, so I put it in the name of the video. Maybe. Let's see. One of these is tangent, the other one's also tangent. So if they're tangent, maybe we have some homothety, like maybe C, L, and J are collinear. Not sure. Let's check that out. Maybe that's true. So wait, what is L? I think L, that was just some point I just drew. Oh wait, how did it draw? Why did it make that black and not blue? Oh, because I made an intersection, not I see. This problem looks a little tricky. Let's see. What does it mean for these to be tangent? A, I, 1B. So I mean, we can kind of define that circle by the in-center x-center lemma, right? So this point should be the center of it. And DI to C, we can do the same thing, right? So let's draw this whole ray. This, let's see. If I draw the circumcircle PCB, this is going to be the midpoint of the arc, and that's going to be the center of that circle. So instead of thinking AI1B, I could kind of think of it as circle AB, the circle through A and B centered at L. So maybe I could get rid of the end circle, and that might make it easier to think about. I kind of like that better. I mean, I guess it doesn't hurt. It just maybe makes the diagram a little more confusing. So if they're tangent, I wonder if the point of tangency just lies on the angle bisector, or if it has to. I mean, it doesn't look like it here, but I don't know if that's just because I didn't draw it exact. So the circle AOB. So the circle DHC, we can kind of just reflect that over BC, right? So it's kind of like and then the circle AI1B. I wonder if it's like a root BC inversion about point P. Like, yeah, the only thing is ABCD isn't cyclic, so that's what makes this tricky.
Yes, I agree. Root BC inversion makes sense to do. But yeah, it is pretty weird, the problem. Just because A, B, C, D are just random.
Yeah. I wonder if these concur. I don't think it's true, but let me. No, they don't concur always. So what's the relationship between points O and H? I don't think really there is a great relationship because, yeah, A, B, C, and D are random.
Can you try to draw the circle with diameter PH?
Sure.
Oh yeah, I just thought that the point of tangency lies on that circle.
Or you thought point B might lie on it?
No, the point of tangency between AI2B and DHC.
Okay. Yeah, if ABCD were cyclic, this would be easier, but then yeah, I do a root BC inversion about P or something like that. Maybe just a normal inversion.
You know what's interesting, actually?
Yeah.
Maybe we can assume that PAB is isosceles.
So why do you think that?
So it seems a bit weird, but we kind of really need just the point L to get that circle AI1B.
Yeah.
And like everything is the same if we took that circle and intersected it with so that circle has two intersections with PC and PD.
Yes.
And like we can change triangle PAB and the problem should stay the same, right?
So we just pick a random point L on the bisector, and we can move it, and then we can just make a circle of any radius about point L. Is that kind of what you're thinking?
Well, that is a good idea, but I wasn't really talking about that. I was just saying that we can, instead of where point B is, we can pick B to be the other intersection with the circle.
Okay, so start by defining points L.
No,
and
actually, that is not true. I'm just, yeah. I made a mistake. Okay, but yeah, it is a good idea to pick L and then take the radius such that it is tangent.
Okay.
Then we can actually, I think we can construct the problem.
So wait, so what's your idea? So we define points L and A first, and then based on.
No, we just define point L.
Okay.
Any point on the angle bisector.
Okay.
And then we need the correct radius of the circle such that it is tangent.
Okay.
We can do that easily, actually.
Okay.
We just need to find the center of DHC and then intersect L and that center with the circle, and that's it, I think.
Okay. So,
what I suggest for now is to erase A and B, and they're not variable points in the problem. Instead, P would be a variable point.
Okay.
Kind of, if you have A and B as the blue points in the GeoGebra, you cannot draw it.
So P would be what point?
So P is just any point. So PDC is the main triangle.
Okay.
And then L is just the variable point on the bisector, and then we draw the circle.
Okay. So that would mean L, the tangency point in Q would be collinear. So basically we draw LQ and we kind of see where it meets the that circle, DHC.
Yes.
And then from there, we draw the circle with the radius LR, and then we could construct the rest of it. Okay, so basically we can draw the diagram exactly. It seems like it at least. So yeah, that gives us a way to draw the diagram exactly. But we still need A and B for point O, right? I mean,
yeah, but you will get A and B after you draw the circle.
yeah, so we're defining A and B to be the intersection of this circle with those two. Interesting. So I guess if we're using that this is the orthocenter, we probably want to use that if you reflect. So the circle DHC is a reflection of circle PDC over DC, right? So maybe we want to reflect this circle over DC because those two are tangent if and only if, let's see, if and only if these would be tangent, right? And maybe this passes, maybe these concur if I draw the diagram exactly. So yeah, I could try drawing the diagram exactly and I could see if these concur. So if I reflect A and B over that, if I reflect I1 over that, what if I like reflect this the other way? Yeah, I'm not sure how helpful all that is. Do you want me to draw the diagram exactly?
I think it will be helpful.
Okay. Whoops. So I'll start with just PDC. Delete. Oh, whoops. I started with, so yeah. Let's just start from scratch. So we have triangle PDC. B is P. And then we draw the angle bisector. Okay, so we start out basically using the in-center, x-center lemma. This is going to be I2. Whoops. And we call this X. So then we want to pick another arbitrary point. And so we're saying, let's draw this circle right here. It's tangent, and let's make it intersect the other sides. So let's call this L. So how did we? I forget how to do this because. So we have AI1, see VI2C, and AOB. So wait, I forget. Oh, I think we draw DHC first. I think that's why I got confused. First we want to draw H. But I mean, really, we could just reflect the whole circle over DC. But I'm just going to draw it anyways. What did I do wrong? Oh, did I do anything wrong here? Triangle center. Number A.
We don't have A, B, and C.
So it should be P, C, and D. So that would be H. And I draw this circle CHD. So AI1B should be tangent to that. So okay, so then we pick a point. How exactly does it work? So we pick a point L. I mean, that would be I2 basically, right? And then we draw the center of this. And this should be how we do it. Yeah. Yeah, I want to make these lines not overlap as much, but it's a little tricky. Okay, so it's not going to be perfect, but basically, so we're going to do it like this. And then we could make like this A and this B maybe. So we could call this A and this B. I think we want this to be A, right? So let's check that actually works.
No, G should be A.
G should be A.
And it isn't I2, but the midpoint of arc.
Okay. Whoops. Sorry, I'm screwing up here. Okay, so G should be A. Well, this Y. Y. So this would be the midpoint of the arc. So this we could call it L. So we have this, and then we would draw the in the center, which we could do this way if we want. Oh, that circle's already there. You're right. So this would be I2. Now this would be I1. And this would be I2. We have AI1B. This our tangent, if and only if, so let's draw the center of this circle. So this circle's a little bit low. Let's see, but that looks a little better. We call O the center of this. We have AOB and that. So this is interesting. So one is tangent whenever the other is tangent. So if we move L, then one of those points of tangencies remains the same, but that point moves. So basically this circle is like rotating kind of. Um, maybe there's something special. It almost looks like FG is perpendicular to AB. I'm not sure that's, no, it's not true in general. Maybe there's some kind of homothency, which, so we're saying if these two are tangent, then these two are tangent. Like, I wonder if the similarity ratio between these two is the same as the similarity ratio between these two. I mean, maybe this looks a little bigger, but we could check that. So let's see. Oh, what did you find?
Well, I kind of find a point which the AOB and DE2C are tangent using the other tangents. I did some reverse angle chasing, and I claim the point is the center of the roto. I don't know how it's. I can say it in English.
Orthocenter.
It's spiral similarity. No, so yeah, it's a spiral similarity. It's the
Okay.
center of the spiral similarity that sends AD to BC. It's the point of intersection of A, wait, ADF, AFD, and CFB. I think it's this point.
AFB and CFB.
I think the point of tangency of the circles is that one.
Interesting. So it looks like that point of tangency is the center of that spiral similarity.
I can explain the motivation behind it, but I'm gonna chat because my English is not very good.
No, it's all right. It's I can understand it. No, that's a good observation. So basically, BGFC would be cyclic and AGFB would be cyclic. So maybe we could redefine things. So yeah, maybe it's easier to define G that way as the center of the spiral similarity, and then we could show that those circles are cyclic and tangent.
I think there's no need in doing this. We can just let the intersection of these two circles be G, and then we prove that AOB is in the circle. I mean, you don't need these circles more in the problem, the AOB and D2C. We're gonna prove that in fact is cyclic.
Okay.
I'm gonna send in the chat some part of the angle chasing that I did in the paper.
Okay. So we define G to be the intersection of this circle and this circle. And then we show, basically from there, we show that DI2GC is cyclic, and we show that AOGB is cyclic. And then, this is interesting. I'm going to make this just a segment for the time being.
I mean, you know angle DFC, right? Is angle DFC is the complementary angle of P, because P equals
Yes, because when you reflect F over DC, it lies on the circle.
yes, perfect.
Or
So we just need to find the other angle, right?
yeah. Okay, so let's think about that. We want to show AOBG is cyclic, and the other one we want to show that is cyclic is I think it's DI2GC, right?
Okay, I'm not sure exactly what you did, but yeah, I angle traced that G lies on the circle.
So this one?
So G and not that one, the other circle.
Oh, okay.
Probably Miguel did the same thing, but yeah, that part can be angle traced at least.
Okay. And then for AOGB, let's see. So AOB is twice APB, and AGB that would be ADF or PDF plus PCF. Yes, okay, so I can also angle chase that AOGB is cyclic. So yeah, you can angle chase that both of those are cyclic. And then you want to show, so basically we kind of define the problem so that these are tangent. And then using that, we want to show that these are tangent. Okay.
Maybe proving the tangency is not hard now.
Yeah, now that we have these circles. What if I try drawing the tangent line to both of them? So can I do a homothency? But yeah, it was a really good observation that these are all cyclic. So yeah, how do you show two circles are tangent without using a homothency?
You have the angle condition for the tangency.
So do you draw like the tangent line to both circles?
Yeah, you can draw it, and So you draw it for one circle, the tangent line, and basically you want to show that it is tangent for the other, and then you just need to show that angle BGC is BAG plus GDC.
Okay.
So that is the angle condition for tangency, and I think it can be angle chased.
Okay, BGC. Basically, if you show BGC is BAG plus
GDC.
GDC, then that would prove that the circles are tangent.
Yes.
Interesting. That makes sense. Okay, so once we know that this is cyclic, that's kind of an angle chase.
Yeah, but we also have to just remember that the problem is
we can use the other tangency, right? Like angle ABF plus DCF is equal to AFD, right? Using the tangency, the first tangency. I mean, you can do it again.
So you're saying, like, if I draw this line right here, we could kind of do the same thing to prove the other direction. Interesting. Okay.
Yeah, you can try the same thing, and it looks much more easier to prove the other angle sum.
Okay, so let's first assume that DHC and AI1B are tangent. Then we could do the angle chase to show that those are tangent, and then we could try to do it in reverse. So
yeah, the proof can be done in reverse for sure.
Yeah. Okay, so suppose. Okay, so first I'll define point G. So let G be the intersection of the circles AFD and BFC. Then, so I'll show you the angle chase that I use to show that AGOB is cyclic. So AOB, let me write it out. So yeah, that's really nice. So AOB is twice APB, and AGB how did I find that? So for that, I think I just said AGB is so it's AFD intersect BFC. So that would be a 180 minus AGF minus FGB, or 360 minus those, which is angle ADG plus angle BCF. Which is 180 minus angle DGC. Let me think about this. So ADG, so PDG plus PCG. I thought I had it for a sec, but now I lost it. So give me just a moment. So AGB, it's 360 minus that, which is that plus that. So PDF plus PCF. Which is 180 minus FDC minus FCD minus angle P, which is 180 minus 2 angle P. Okay, I got it. So I'm going to write out, first I'm going to write out the angle chase that AGBO is cyclic. So it's a little complicated, but we have angle AGB is 360 minus GF minus angle FGB, which is equal to angle which is 180 minus BC minus angle P, which is 180 minus 2 angle P, which is 180 minus angle AOB, and that implies AOBG is cyclic. So we have one circle there. Okay. And then should I just say, like, by a similar angle chase, the other one is cyclic? I could just leave it to viewers. So by a similar angle chase, DI to GC is cyclic. Yeah, it's a lot of angle chasing, but yeah, finding that G was the Miquel point is a big observation. Or the center of the spiral similarity. So so I'll say first assume that AIB and DHC are tangent. So C are tangent. Okay. By drawing the tangent line at G to AOB, we find that basically AOB and DI to C tangent if so the angle condition is BGC equals BAG plus CDG. So that's BAG plus CDG. I'll just say which is easy to angle chase. I'm skipping some stuff, just so let's think about that, because BGC is BFC. I'm guessing that's how we start out, right? And then if we know that these are tangent, then BFC would be YF plus CDF. So basically, if we know that these are tangent, then BFC is BYF plus CDF. Is that kind of how you were thinking about it? Or BAF plus CDF? So yeah, I think it might just be trivial. Yeah, because, well, so if these are tangent, then BFC is BYF plus CDF. BFC is BYF plus CDF. Oh, so maybe these are both if and only if. So maybe that would just kind of solve the problem. So these are tangent if and only if that's true, and these are tangent if and only if that's true. And maybe if you assume this, you can show that, and if you assume this, you can show that, because is that right? So CDF is not, it's not like this equals that and this equals that. So there's something to show. But if you subtract the two, so CDG minus CDF is FDG. And if you subtract these two, BAG and BYF, that would be BAG and BAF. The difference is GAF. So yeah, basically by subtracting these two, it's like the same as saying GAF is like GDF, I believe, which is true. So so it's easy to show that these angle conditions are equivalent since AGFD is cyclic. By subtracting them and using that AGFD is cyclic. So yeah, I think this is right? All right, so we can move on to another problem. But yeah, that was a really great idea, drawing point G. So we only have like 4 minutes left. We could just draw this one. So this is like an isosceles triangle. We'll probably just have enough time to draw it, but let's see. So AB equals AC, and then we have midpoints of BC, AM, and AC. And we have M. and N. And then we draw the circumcircle of AMC. And we see where it meets AB. So that's just like the foot of the altitude from C. And E. And meets BL at Q. And then we draw the circumcenter of BQC. Looks like, does that circle, oh, BQC, sorry. BQC. It's centered at O. And O is going to lie on AM. And then AC and PQ intersect at some point at X. It's a weird problem. OB and LN meet at Y. So this is X. OB and LN meet at Y. So LN is the mid segment of the triangle. And BQ and CO meet at C. Interesting. So those might intersect a little bit far away. So yeah, those intersect like very far away the way I drew the diagram. But see if I can maybe shrink things so it's not so far away. So that would be X, Y, and this would be Z down here. Waiting for this to go away. Yeah, I wish I could disable this thing. It's Z. Interesting. And we want to show that those are linear. I wonder. Okay, so I was going to say maybe CX equals CZ, but so yeah, we just had enough time to draw this, but yeah, we're not going to be able to solve it probably. Unless a miracle happens. So it's interesting. So yeah, I don't know if it's Desargues theorem that we could use, or what would the triangles be for Desargues theorem? So we have like PQL. I could just draw it really quickly before we finish. So PQL. That's weird. It didn't draw it like it was filled in, but okay. So triangles PQL and triangle. I don't even know which one. So BO. BO. Yeah. I'm not sure. But yeah, we could figure it out another time. But anyways, yeah, thank you both for staying till the end, and yeah, we had some very nice solutions. So for everyone watching, thanks for watching. If you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.